Here are all the definitions we're going to be working with. We got a population. Population is a group, not a number. It's the group that we're trying to find something about. If I wanted to calculate the average height of all women in the world, then my population would be women. And the population parameter I'm trying to figure out is height. So a parameter is the thing about the population, the number about the population you're trying to figure out. Problem is, there are 3.5 billion women in the world. I don't have time personally to go and get my tape measure out and measure every single woman in the world. So instead, we do a sample. A sample is a small subset of the population that you actually study. You want to study the population, but you're too lazy to do it, so you do a small sample instead. If you were to do a sample of the entire population, we call that a census. We just did the US Census this year, and that is a sample of the entire population. Now, technically, the US Census doesn't get to everybody. Not everybody fills it out. I don't know what the numbers are, but I would guess it's probably something like 95% coverage. So it's actually, the US Census is actually just a really, really large sample, but that's as close as you're going to get. The sample survey are the questions that you ask your sample. So if I were trying to find average height, my survey would be, what's your height? This is one question. These two confuse people, parameters and statistics, because you have in your head that this word parameter means like a limit or a bound. And that's not what it means in this class. It just means it's a number that came from your population. Population mean, the median, the 75th quartile, the max, these are all population parameters. Any number associated with your population is called a parameter. That same idea, but coming from your sample, we call a statistic. So your sample mean would be a sample statistic. Notice the P's go together and the S's go together. So we want to figure out a population parameter. I want to know the average height of all women in the world. I don't have time to do a census. That would be too hard. So I do a sample instead. I calculate my sample statistic, the average height of women in my sample. And as long as my sample was good, hopefully this number is close to the thing I'm actually after. This is what I want to know. I'm too lazy or it's too hard to calculate it, so I find this and I hope that that's close to this. Problem is, it's really easy to do bad samples, samples that don't look like the population. And we call that sampling bias. So the word bias, you have in your head something intentional, that you're a biased person. That's not what we mean, or that's not all we mean in sampling bias. Sampling bias is there's just something wrong with your sample. It doesn't look like the population. If I went to an elementary school and just measured the heights of all the students, that would be a terrible sample because I'm measuring kids. They wouldn't have the same heights as adults. That would be a biased sample. And we'll talk about different kinds of bias in a minute. And then this is a very important topic here. Let's say we all go out and we all do great samples. I send each one of you out and I say, I want you to randomly find 100 women worldwide. Take good samples. Make sure your samples look like the population. Calculate your average height. I send every one of my students out. I've got 200 students. They're going to come back with 200 different samples that look different. Samples vary. If we go out and we collect a whole bunch of samples, none of the samples are going to match. They're all going to look a little bit different. But then we hope that most of them look like the population. We have this thing called the central limit theorem that says our samples will be normally distributed. Some of them are much higher than the population. Some of them are much lower, but the average of all our samples will match the population. That's what we're going to talk about next time, the central limit theorem. But just keep this in mind always. Samples vary. Okay, so this is literally the example I just talked about. We want to calculate mu. Remember, mu, Greek letters for population parameters. Arabic letters, our letters, for sample statistics. So we want to calculate the population mean. We don't have that. Mu is the population mean. We go out and we do a sample of 1,000 people. We try not to get a biased sample. We get from our sample the sample mean X bar. Greek letters for populations, our letters for samples. X bar means the sample mean. We hope that this number we calculated is close to the thing we're actually after, this population parameter, mu. Okay, now there are dozens of different types of samples. I'm not saying these are the only types of samples. These are the types we study in this class. So we've got 5 of them: simple, random, convenient, systematic, stratified, and cluster. So these last 2 you're going to get confused. So I'm going to spend extra time on them. These first 3 are pretty easy. A simple random sample is you put everybody's name in a hat and you randomly draw out 50 names. Everybody in the population has an equal chance of being in the sample. This is the best kind of sampling you can do. It eliminates all kinds of bias. The problem is this is hard. If I wanted to do a simple random sample of the world's population, then I would need to create a list of all 3.5 billion women, create an Excel spreadsheet, assign a number to each of them. So I've got an Excel spreadsheet, 3.5 billion entries long, use a random number generator to generate, 1,000 numbers, go through my list, find those 1,000 women, and then fly all across the world to those 1,000 women and measure their height. That would be impossible. So that would be best, but that's really hard. On the flip side of that, the worst kind of sample you can do, a convenient sample. Convenient sample is you stand outside Publix and you talk to the first 50 people that walk by. It's really convenient. You didn't have to do anything. The problem is you're probably not going to get very accurate results. Say, for example, I wanted to calculate average income in Orlando. Do you think going to Publix and standing there and asking people as they walk by, hey, how much money do you make? Would that be a good sample? No, we're at Publix. Publix is more upscale than, say, an Aldi or a Save-A-Lot. So sure, it was convenient, but my sample won't look like the population. A systematic sample is you follow some kind of mathematical pattern. You stand, let's say we wanted to calculate average GPA on Valencia campus. So we stand in one spot and we talk to every 7th person that walks by. Or we get everybody's ID, and you guys have an ID number, your VID. We talk to everybody whose VID ends in 3. We're following a mathematical pattern. That's called a systematic sample. You're following a system. Okay, these next 2 are the ones you're going to get confused. Stratified and cluster. In both of these, you put everybody in a group. In stratified, you put everybody in a group so that they share some common characteristic. So your groups all look different from each other. Then you take a small sample from each group. Cluster, you put everybody in a group, but each group is a mixture of people. It looks like the entire population. And then you talk to entire groups. Cluster is talk to a few entire groups. Stratified, talk to small samples from every group. So here we've got our population separated out. I've got the blues, the reds, the greens. These are my different strata. And then for my sample, I took one of the blues, two of the reds because they're a bigger group, and one of the greens. Now this is my sample, and it's a mixture. It looks like the whole population. Cluster, I put everybody in groups, but each group is already a mixture. And then I grab, say, these two entire groups, and now my sample is a mixture. It looks like the whole population. Okay, so say we wanted to calculate average GPA. So I put all the nursing majors in one corner, all the engineering majors in another, and and I separate everybody out by their GPA. And I grab 5 nursing majors and 7 engineering majors because there are more of them, and 3 math majors and so forth. That's building a stratified sample. Everybody's in a group where they share some characteristic. If instead, I put everybody in your, this makes more sense when we're on campus, but on campus we've got 8 buildings, and each building is a mixture. Say I waited until noon and I talked to everybody in building 1 and everybody in building 7. Then each building is a cluster that's a mixture of everybody, and I talk to entire groups. That would be a cluster sample. Another example, say we want to calculate average income at some large company. So I sample 2 vice presidents, 4 custodians, 7 from the secretarial pool, and so forth. That's stratified because I'm talking to small samples from distinct groups. If instead, say my whole office building is a mixture, and I talk to everybody on floor 1 and everybody on floor 5 of some big giant building, that would be a cluster sample. Okay. These will make more sense as you do that assignment that's due in a couple of days, and try some of these on your own. Okay, and then here are some types of bias. You won't get tested on these. These might show up in the homework. These show up on the test, but the types of bias don't. These are just interesting and things you should be thinking about. Voluntary response bias is you send a survey out to everybody and not everybody replies to it. Only people that really care one way or the other respond to your survey. Then you end up with what's called voluntary response bias. You get a biased sample. Like American Idol suffers from classic voluntary response bias. I don't even know if that's relevant anymore. I've never even watched the show, but the only people that call in and vote on that are ones that really care. Or Rate My Professor is notorious for voluntary response bias. I've been teaching for 20 years and I've never gotten a Rate My Professor that said, he was okay. Only people that love you or hate you bother to fill it out. Non-response bias is kind of the flip side of that. These two go hand in hand. Non-response is you send your survey out to everyone and some important group just didn't even reply to your survey. So if I send out a poll to everyone trying to do something to improve your grades, and all the people that are doing poorly in the class already didn't even respond to my survey, then I can't trust my results because they were the ones I was trying to help to begin with. That happens all the time. Notice these all have the word response in it. I didn't name these. I think that's silly. Response bias is different than these, different from these. Response bias is you're asking the wrong questions. These are you're asking the wrong people. These are you're asking the wrong questions. This is almost always intentional. If you get, now it's political season, you're going to be getting phone calls of people doing surveys, and you're going to get a lot of response bias. You're going to get people asking loaded questions so that they can force you into saying the response they want you to say. So, like, I'm just going to make something up that's apolitical here, but say somebody wanted to do a survey on Burger King versus McDonald's, and they might call you up and say, which do you prefer? The delicious flame broiled taste of the Whopper or the terrible soggy taste of the Big Mac? So they're asking the question in a way to try to force you to say the Whopper. And it's almost always intentional. So then you can't trust their results. They publish some result that says 84% of Americans prefer the Whopper when it's really not true.